Hello, everyone. Welcome to another session of the RoboLaunch October series. Today, it's our pleasure to have Wenshan Wang. Wenshan is a system scientist at CMU, where she works in the Air Lab with Professor Sebastian Scherer. Wenshan is interested in understanding and modeling intelligence and developing autonomous robots based on that intelligence model. She's currently working on improving the autonomy of robots by utilizing learning-based methods, including supervised, unsupervised, semi-supervised learning, and reinforcement learning methods in a variety of applications, such as drone filming and SLAM in dynamic environments. Wenshan received her Bachelor of Engineering from the East China University of Science and Technology in 2009 and her PhD from the Shanghai Jiao Tong University in 2017. Before becoming a systems scientist, she held a postdoctoral position at CMU from 2017 to 2019 and a project scientist position also at CMU from 2019 to 2023. So without further ado, please mention, the floor is yours.
Thank you. Thank you for the introduction. So as in an introduction, so I'm part of the Air Lab. So Air Lab is quite a big lab. So we have a lot of talented researchers, students, so collaborating together. So today I'm mainly talk about the research recently has been done in Air Lab and also highlight some of the achievements and the interesting technologies we developed for different applications. Yeah, it's mainly high-level introduction. So if you have any questions, feel free to stop me or ask the question at the end of the presentation. And so the first thing I want to highlight is that, so we are, sorry, the slides is jumping around. So yeah, this is just a quick snapshot of a variety of projects we have done recently. So we developed field prototypes in very challenging environments without GPS guidance and without teleoperation. So these are different applications like subterranean search and rescue, and wildfire detection and prediction, and infrastructure inspection. So we often focus on safety critical tasks and in those very challenging environments. So we are very experienced in designing, integrating, and developing robust prototypes for ground and area robotics. So here are some platforms we developed and been working with. You can see there's a lot very diverse of robots, like different types of drones, different sizes of drones, and ground vehicle also in a variety of sizes. So we also focus a lot on the real world tests. So we have very large testing sites. As shown in the left side is a Cascola testing site. So it's a few kilometers in diameter, and it's all like off-road settings with all kinds of challenging terrains. So we are testing and developing the off-road driving system in this testing site. On the right side, it's an abandoned hospital environment, which has a combination of indoor and outdoor scenes. So we test a lot of the drone and this legged robot in these environments. Here I highlighted a few projects we are working on. I'll show more videos in the next slides. So Professor Sebastian Scherer led the DAPA sub-T challenge a few years ago. So our team Explorer has won the first and second place in a couple of competitions. So here shows the video of the competition. So the goal is to search for a few predefined objects like a human, like a cell phone, like a backpack in this complex environment. So we'll send a team of heterogeneous robots. Like here we have a drone and a ground robot. The drone just take off from a ground robot and explore the environment collaboratively with the ground robot. So in these environments, typically it's very challenging in terms of the perception and also the planning. Here you see when the drone flying, it kicks off a lot of dust in the environment. So it's pretty challenging for the LiDAR localization or visual localization in this dusty environment. And also how to collaborate more multiple robots efficiently so that they can explore different areas given their own capability is also a very challenging problem. For example, we want the drone to explore like challenging environments like vertical environment that cannot be reached by the ground robot. And different robots need to share the information with each other. For example, the map built by one robot can be shared to another robot, so it can use the map to adjust its own estimation and to make better decision. So here it detects the backpack and the fire extinguisher on the wall. And it will send those information back to the human operator to confirm and to give feedback. So here show another example. So this is also sub-1 sub-T, but in a cave environment. It's a little different than the previous one. The cave has more challenging features. You can see there's a lot of dusts here. Also, the shape of the cave is more complex. So some tunnels are more narrow, so it requires better planning techniques as well as more robust state estimation and perception. So another interesting work we've done is how to use fewer example like to learn how to detect novel objects. So usually, using machine learning, you need large amount of training samples. Like you need a human to label hundreds or thousands of images of the same type of object in order to learn a robust detection model. So here, so we developed a few shot detection model. So that requires no fine-tuning on the real data. So it can detect the novel object by just showing showing it with 3 examples. So it is trained on a large data set and validate directly on this sub-T data set. And we can see it performs quite well, like without any fine-tuning. So that, yeah, in this case, it's very important so that human can just show a few examples of which object you want to find in this environment. So the drone or the ground robot can just be deployed to find that object without like labeling hundreds and thousands of images. So as I just mentioned, so in those challenging environments, we really need very robust state estimation and SLAM technique. So here I showed the super odometry developed by our lab. It's a multi-model SLAM framework. It basically combines different sensing modalities. So you can see here in this test, the drone is out of control, so it's spinning very fast. But you can see the tracking result of the super odometry still, even in this fast out of control situation, it can still track the trajectory of the robot. And we also test this pipeline in the smoke environment. So yeah, the key idea is to take advantage of multiple sensors. For example, LiDAR is generally more accurate in most of the situations, but when you comes to a long corridor, it will have this geometric degradation problem. But vision sensors can compensate that problem in this long corridor environment. In the smoke environment, both LiDAR and visual sensors will be affected, but we also have a thermal camera on the drone so that it can see through the smoke more like reliably. So we also use the super odometry on this ground vehicle that's driving very fast in this off-road environment. Yeah, another key idea about the super odometry is that it relies on the IMU sensor to provide a reliable pulse estimation. So the IMU sensor is measuring the robot's acceleration and angular velocity. So it will not be affected by the environmental degradation. So yeah, it can provide relatively robust measurement. So another line of research we have been looking at this vision-based SLAM algorithm. What this means is that we want to move away from the LiDAR sensor, which is very heavy for the drone to carry. And also the LiDAR emits a lot of signals. In a lot of application, you want a passive sensors like camera so that you won't be detected by other people. So here, so we develop a vision-based state estimation and mapping module that can take a stereo image and estimate the robot trajectory and create a map like here in real time. So yeah, this shows, so here's more example of the map generated by this one. So you can see on the left side is a first-person view image and the depth estimation. So on the right side is the 3D reconstruction of the environment. So you can see very in high detail the types of the terrain, the gravels on the terrain. So the resolution is also is much higher than typical LiDAR sensor can view. Yeah, so here is just a few example of more example of the how the mapping look like. So we first build a 3D reconstruction, and for this off-road scenario, we project the map to a bird's eye view so that we can do planning and the cost estimation on top of these maps. So to enable a good driving, autonomous off-road driving performance, so we need to model the dynamics of the vehicle very well. So the typical, like the traditional way is to reason about the kinematics and dynamics of the vehicle. So a typical model is the kinematics bicycle model, which take into account the vehicle's kinematics. But in general, it is very hard to model the vehicle dynamics in this off-road driving project, in this off-road environment, because the terrain is so complicated. It has different features. For example, if you drive on the flat terrain versus a bumpy terrain, your behavior will be very different. Also, there's all kinds of grasses and the different lengths of the bushes. So those things will change the terrain, friction, the dynamics a lot. So that we propose here a learning-based dynamics model that doesn't only take account of robot kinematics and dynamics, it also takes into account of the environment feature. So we depend our dynamics model on the top-down view RGB and height map, and which can be used to predict more precisely and reliably the vehicle's future dynamics. We integrate this model on the vehicle, and we can show. So here, the model can predict not only more accurately than the KBM and the other previous models, but it can also generalize better to different velocity and yeah. So here we showed we implement the neural network based prediction model on the vehicle and drive the vehicle with very aggressive maneuver. And this blue lines is the output prediction of our neural network. Yeah, it generally predicts like more precise trajectory than the baselines. So another interesting problem in this off-road driving is how to estimate the traversability cost. So you can see here, it's very muddy, and from the LiDAR or geometry, you can see very similar, right? So you cannot really differentiate where is drivable and where is not by just looking at the geometry. But human can differentiate, like this green terrain might be safer because it looks more solid, and the red box, it may be more uneven and has puddles of water. Maybe they feels very different. So we use the same idea. So it's hard for human to label, but we can actually predict how the vehicle feels about the terrain by looking at the IMU sensors data, like while it's driving through all kinds of terrains. So we can see here, one on the left side is quite bumpy terrain, and on the right side is quite a smooth terrain, and you can see the IMU acceleration is very different. So we use this as a supervision signal. So we developed this self-supervised traversability estimation that looks at the local map and predict the cost based on the IMU data. So here's a visualization of what's the terrain cost we learn. So you can see on the one side, there's a bumpy terrain. So on the left side and on the right side, it's more smooth, and kind of you can capture, our cost estimation can capture this difference. So these four predictions are the cost estimation on the different velocity. So this is 2 meters per second, 4 meters per second, 8 meters per second. You can see it naturally predict like higher cost, traversability cost when you drive faster. So also to predict the traversability cost, we also looked at how to recover the cost based on human demonstration. So this is another supervision. So we can get from a lot of driving data. So we don't need a human label, but we can learn from a lot of human demonstration, like a human just to drive around the different types of environments for a few hours, and we can recover the human preference of the terrains just by looking at how they drove. So here's a general idea. So for example, the green line shows the human demonstration in this type of terrain. Because we drive, we assume that we drive in a very diverse manner. So it can be different trajectories in the same environment. So we can see there's a couple of green trajectories. So the assumption is that humans just prefer trajectory that has lower cost. So human drive safely, so that the trajectory human selected should be with very low cost. And then we can also randomly sample a few trajectory, or not randomly, we can just sample a few trajectories like the red trajectory shown here. And because the red is different from the green, so we will assume that the red trajectory has higher cost. So we simply use this idea to train a model to predict the cost based also on the top-down view maps. Yeah, so using this method, we can also recover the cost, traversability cost in this challenging environment. So here show the example that we recover the cost, and we drive the vehicle in all kinds of terrains with very long period, and it can drive safely with a higher speed than the baselines, like with less interventions. I'll skip this. yeah, we can show that with this learned custom map, the vehicle has more intelligent behavior, such as it can make shortcuts through drivable grass and avoid high risky areas if it's too dangerous. We can also tune the like risky level because our model is a probabilistic model, so that we can tune how much risk tolerance you want to have in each test. So yeah, the previous one is for off-road driving. So we also did a few projects on infrastructure inspection. So yeah, it's quite a dangerous work for human to inspect bridges and buildings. So those bridges are typically very high, and it's also very tedious work. So that the people need to take pictures of the bridge and cover the bridge to detect any cracks on the bridge. So we're trying to use drones to make the problem, to solve this task autonomously, so people don't need to risk their lives. So during the 4-year research, collaborated with infrastructure engineering company. So we built several specialized sensors, so like shown in here. And this robot can just take off and autonomously take pictures of the infrastructure and try to can recover the mesh and high resolution model so that it can be analyzed with this software to detect any cracks on the infrastructure. So here show a nice. So here shows a process of this algorithm. First, the drone will fly autonomously, take high resolution stereo images. It will build a 3D point cloud of the structure along with this high resolution 3D models. So it will also recover a mesh and fill the holes if necessary. The reconstructed data can be utilized for inspection purpose because it's in like sub-millimeter accuracy. You can detect the cracks and also analyze the force of this structure. Yeah, you can use it with some commercial software like FEM simulation to detect any deficiency in this structure. Yeah, I think that's the last thing I like to share. So this is our team. So we have a lot of people. Yeah, any questions?
Hey, yeah, thanks for the awesome talk. Well, we can start the Q&A now. I have a couple of questions. The first one is, thanks for the awesome talk. The lab work seems to be very focused on applications, so I'm curious about how much of the lab work is transferred to the industry. Thank you.
So yeah, we have a lot of collaboration with industry and military. So yeah, you're right. The lab is very focused a lot on the application because we think the application will tell us what the most interesting research problem is. So, but we also research a lot of interesting I was trying to answer a lot of difficult research questions, like how to do better, like more robust state estimation perception in those challenging environments. So I think, yeah, that's a really good combination of research versus application there. So in terms of the transfer, so I think a couple. As far as I know, a couple of students that graduate from our lab has been been doing the startups, like they're trying. I think I remember a group of students has started a drone startup on using drones to maintain the warehouse or storage inspection, like those applications, and some of the application also like drone delivery. Yeah, there's quite some interests. So I haven't talked about the more recent project on the wildfire detection. So in that front, so also a group of students also thinking about starting a new company like on that topic. Yeah.
Awesome. Yeah. Yeah. There seems to be a lot of transferability indeed. So I think the next question kind of touches a bit on what you mentioned. Is in these harsh environments, such as caves, what component of the autonomous stack tends to fail more frequently? Is the state estimation, the planning, the hardware, the perception?
Yeah, actually, all of them will have a tough time in those challenging environment because of the current way of design these systems. You know, the current most common way to design these systems are all modularized, right? You have a perception and planning control pipeline, right? So usually if the perception give or state estimation gives a bad estimation, your planning and the control algorithm will also suffer, right? Because it's like this is like a pipeline. So I would say since state estimation and perception are the foundation of the planning and control, so that probably makes biggest difference. Yeah, if you can improve the robustness. Uh, Also, we are also investigating a more coupled pipeline instead of doing state estimation, perception, planning, control. We want to see if we can develop a more end-to-end system so that every modules can be tuned and updated in a joint manner, so that you don't have this modularized way, and different modules can collaborate with each other, cooperate with each other better. That's more a research direction. So I think the most practical system are still modularized.
Thank you. So next question is about the traversability estimation. I understand that we use the IMU measurements as a ground truth data for the camera images in the self-supervision process. I wonder if this approach works well in more muddy terrains, where I would assume that the IMU output would be quite smooth, even though the terrain is very difficult.
Mhm. Yeah, that's a good point. Yeah, I think we haven't looked at the multi-terrains because it's also very dangerous to collect the data on those terrains. So yeah, the vehicle is generally easy to get stuck in those terrains. So in the current work, we mostly looked more into like traversable terrains like grass, gravel, and smooth terrains. yeah, I think to detect those muddy area, to how to estimate the traversability in those areas is very interesting question. So in that one, we probably can look into the difference between your state estimation and maybe your wheel encoder estimation from the wheel to detect those wheel slipping or other issues of the terrain. Yeah.
Thank you. And this is a question more about the lab, very general question about the work of the lab. Does the lab have work exploring reinforcement learning for controls and dynamics?
Yeah, we looked at some of the reinforcement work at the beginning of this off-road driving project. It turns out it doesn't work very well if we just apply them end-to-end, like train end-to-end model using reinforcement learning. So I think we plan to come back to reinforcement learning more in the future after we have already developed this better dynamics model and also a better model of the terrain. So I believe instead of end-to-end learning, like from the first-person view image or sensory input to action, we should use reinforcement learning in a more a smarter way. For example, taking only first-person view image would not be very good idea because it cannot generalize between robots, right? Different robots have different sensors, and the sensors are mounted differently on different robots. So even changing of the mounting angle will totally destroy the applicability of the model. So I believe instead of the raw sensor inputs, we can look at the top-down view map or other like more generalized abstract representation of the environment so that the model can be generalized. Yeah.
Okay, thank you. And this is like a question from me that like an extension of this one is in the lab like in these applications, do you tend to rely more on model-based controls or some kind of model-free control? And because something that I learned recently in one of these talks is a big advantage of model-based controls can be precisely the generalizability, because if you have another system and you can write down a different model, you can use the same thing for a different model. Is this something that the lab tends to explore? Is that,
Yeah, I agree. Yeah, I agree that model is very important in these planning and control models. Yeah, so I think that's one reason that we spend a lot of time looking at this learning-based way to develop more generalizable models. Yeah, so I believe we do need to understand the dynamics, the model of the environment before we can develop a good planning and control model.
oh, great, thanks. And now we'll switch gears to some questions more related to race and grad school advice thing. The first one is regarding the risk projects that students are usually involved with. Are they more focused on the theory, for example, developing new algorithms, or the implementation itself, or a mix of both?
I think it's a mix of both. Yeah, we have we had collaborated with so many RES students in the past few years, and different projects also have different flavors. So I guess it also depends on the interests of the students. So usually there's no one one rule, like whether we works more on theory or application, but we will discuss and work with the students to figure out what's the best topic and direction for each individual one.
Oh, okay, great, thank you. And the last question before we wrap up is, given the broad range of projects, what's the recommended background of a student is interested in joining the MSR program in the year lab?
The question is, what is
It's
suggestions?
yeah, the recommended background, I suppose, like maybe
Background.
Yeah.
Yeah, I guess so that also varies a lot. Yeah, because yeah, you see there's so many projects going on in Air Lab. So yeah, there's really no like one fit all background requirement. But in general, so we do hope the students can be more self-motivated and can so is willing to explore idea on his or on himself. So, and also we hope the students are willing to have to get hands-on experience with robot and real systems instead of just training models on the data set. So yeah, those are like a general hope like we have for the new students. But in terms of background skill, so it's quite diverse, like depending on different projects. Yeah.
Oh, okay, great. Do you have any final comments you want to add?
Yeah, I'm just very appreciate Rachel and all the organizers to give us the opportunity to share our research and projects, and I hope more people are interested in our lab and join our lab.
Yeah, and also thank you very much for making up the time for us. Thanks for the awesome work, of course, in the lab.
Thank you.